So we can test another alternating series. In this case here, the 1 over n square root n. And again, this one converges to 0 slower than the harmonic series. So we know that this one, the sum of this is also infinite. But what happens to this as we alternate it? So what happens if I change this into, okay, so this becomes, instead of 1 plus, it becomes 1 minus, and then plus 1 over root 3 minus 1 over root 4 plus dot 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 dot, and then we alternate it into 1 plus 1 minus. Okay, so we have our minuses here, the plus and minus, plus and minus. So what it's going to look like, it's going to look like this. So I'm going to go add 1. Okay, now in this case, the 1 over root 2, it's the alternating harmonic series just stops here. Well, root 2 is going to go a bit further. Okay, 1 over root 2, and then we're going to go 1 over root 3, so it's going to, go like that. And these lengths are not going to change as quickly as our harmonic series. But regardless, the same property still happens here, is that the tip of this next arrow never passes the tail of the last arrow. Okay, so we're going to just go back and forth, back and forth, back and forth, and we will converge to a sum. Now, we don't know this sum, okay? We don't actually know what the sum is. We kind of can guess about where it is numerically, but this sum we can't calculate. But we don't really care actually in calculus. We don't care what the actual sum is. What's important is the fact that it converges to some limit, okay? And that limit is all we need to know. We just need to know that there is a limit that's good enough for us. What that limit is actually very, very difficult to figure out what it exactly is. We can get as close as we want decimal wise, but to actually figure out what that number is, for example, like log 2 for the other one, for the alternating harmonic series, well, that takes a little bit more math to do. And this is beyond the scope of this course, and people spend lots of time figuring that out. But for us, we just need to know it's a limit. There's some limit. We can estimate where about it is. The number doesn't matter. The fact that it converges is good enough for us. And so we can, as long as every term gets shorter, we know that all of these alternating series must have a limit. So what can we generalize about series that alternates and decreases to 0? Well, we know that all of these are converging series. And that is what's important to us. Okay, so any alternating series that goes to 0, it must be a converging series, and because it has this property where the next term never can surpass the previous term, and it always converges to a limit. So there's different types of series that we've looked at. Okay, some are convergent, some are diverging. The infinite geometric series, right? When we have 1/2, 1/4, 1/8. This one is, we've already seen this, it's converging. All infinite series converges. Okay, and we generalize it as ARN, so this is our TN formula, and we put it into our sigma notation. The harmonic series, okay, this one here, this one diverges. And this is our boundary series, and we've kind of proven this. We've seen videos of how we can prove that this diverges. But what's important again is, does it converge, does it diverge? For infinite geometric series, we can actually calculate the limit. That really, in the end, is not that important to us. The fact that it is converging is what's most important. The fact that this is diverging is important. The P series, if P is greater than 0, okay, as long as P is greater than 0, some of these converge. We know the harmonic series diverges when P is equal to 1. The basal series, when P is equal to 2, converges. The square root series diverges. So these are some, depending on P, we know that some of them diverge and some of them converge. In fact, which ones converge and which ones diverge? Well, we can say that if P is bigger than 0 and less than 1, it diverges. Okay? But if we have ones like the basal series, where P is greater than 1, actually we can say equal to 1 because equal to 1 is our harmonic series as well. But if P is greater than 1, it is convergent. It converges to a finite limit. So these are some rules now and some generalities that we can use to determine converging or diverging. Looking at this factorial one, well, factorial grows very quickly. Okay? In fact, factorial is our most powerful function that we have so far, even more powerful than the exponential function, which generates our geometric series. So would this one converge or diverge? Well, I've kind of given you a hint. It's in blue. This is definitely convergent, okay? Because if the denominator is much, much more powerful than the exponential function, and that always converges, this one must also converge. Okay, this is a convergent series. This factorial one we're going to see quite a bit later on. So when the denominator is powerful, we know that it's more likely to converge, and the boundary of convergence is going to be that 1 over n function. So this issue of convergence and divergence is really important. The actual sum is irrelevant when it converges. Okay? What is important is the issue of convergence and divergence. And so there's another video here that you can watch, and which kind of highlights this idea of convergence and divergence is important to us in calculus.